Oh, hey, didn't see you there. You might be wondering why I was just playing some Angry Birds. Well, we're moving on and discussing something that we've kind of talked about before called vectors. Um, Vectors are something you may have seen in physics if you took a physics class. It's a mathematical concept that is involved in so many different places throughout all sorts of realistic applications. Um, for example, something like iPad or iPhone game like Angry Birds. Um, what we want to be able to do, though, here with math is to say that we can recognize vectors as having both magnitude and direction. We want to be able to represent vector quantities by directed line segments and use appropriate symbols for vectors and their magnitudes. And we want to say that we can find the components of vectors. Um, I'll bring in some concepts from Angry Birds and some other realistic applications as we start to begin this discussion of vectors. So first thing, we have two types of quantities, scalar and vector quantities. We want to know what's the key distinction between them and consider how we can describe their differences. So let's think of a car and a car's motion. In fact, I'm going to draw this car as a truck, just because I think a truck might be a better way to distinguish where the front of the car is. So this is my beautifully drawn masterpiece of a car here. Say we're traveling in this car and this car is moving at about 10, now we'll go about 70 miles an hour. It's on the freeway. 70 miles an hour is a reasonable speed to drive in a car. Sometimes that's the speed limit. This quantity right here is what we call a scalar quantity. 70 miles per hour is scalar because it's just saying the speed of a car. It's not telling us anything else except, hey, this car is traveling at a speed of 70 miles per hour. But knowing that it's going just 70 miles per hour isn't really that useful to us. We don't know what direction it's going. All we know is this magnitude, its speed. That's where vectors become useful. If we're going to keep talking about a car and its motion, vectors give us the opportunity to look at the motion in a direction of this car. So imagine this is the 10 freeway. Like here's Colton, and over here is like Redlands where I am, and over here is Rancho Cucamonga or something. So the 10 freeway, we have Rancho is to the west, and Redlands is to the east, and here we are in Colton. I totally spelled Colton wrong. Colton? What's wrong with me? Colton. Vectors can give us a perspective on what direction something is moving. For example, if the car is going, or this truck is going to the east towards Redlands at a magnitude of 70 miles per hour, we now know its magnitude and its direction. It's going 70 miles to the east. Another car may be on the other side of the freeway. This car could maybe be going to the west, but at a magnitude of 65 miles per hour to the west. So vectors are quantities that give us both a magnitude and a direction. A scalar has only a magnitude, so write that here. Scalar has only magnitude. But a vector quantity is beautiful because it tells us both magnitude and direction. There are tons of different units of measurement, and some may be a scalar quantity, some may be vectors. For example, things like distance, miles. That doesn't really tell us anything about a direction. Miles is just one single unit. We don't know if it's left, right, up, down. Miles itself is a scalar quantity. But other units need some sort of a direction to it, like a force. Forces are vectors because we need to know what direction that force is acting. Is it acting down on some body? Is it acting in an upward direction? Right, left, forces always have to be a vector quantity. So if it has both a magnitude and a direction, it's a vector. If it's just a magnitude, it's scalar. Mathematically, we can represent vectors graphically. First thing I want to talk about a little bit of notation for vectors. It's different in writing in print, like what you're reading on this paper, than it is by hand on a paper, or if you were to write it on your own note sheet or something. So when typing in print on a computer, like I did for this document, or when reading from like a textbook, a vector will be denoted in boldface. For example, we may consider a vector v. Notice how this v is bold. That's the vector v. However, sometimes you might have to write it on paper, and writing by boldface isn't really an option. So we denote a vector, we'll call it v again, with a little arrow above it. So here's our vector v. I like to draw my arrows with just a little half symbol, half arrow. Some people actually write the full arrow, but for me it gets kind of hard and sometimes I can't really tell what that is. And it takes up too much space. So I like to use just a little, it's almost like a little check mark sideways or something. So this is how I will write my vectors. It doesn't always have to be v. You can use any letter to symbolize your vector that you want, technically. U is common. W is common. So on. Alright, so vectors, when represented in a coordinate plane, we kind of saw this idea with complex numbers. And I used the word vector, but we didn't really talk much about it. Vectors can be represented in a coordinate plane as directed line segments. So let's see what that looks like. So we'll plot 2 points, column A and B. A is at 1, 2, and B is at 4, 6. So this is our point A. Do this blue. It's at 1, 2. And our point B was at 4, 6. A vector starting here at point A, because it's saying we're going, well, it hasn't asked that yet. We just plotted the 2 points. Next, we want to draw a vector. We'll call it V from point A to point B. So point A to point B. We're starting at A and ending at B. When we say it's a directed line segment, that means we need to specify the direction of it. To do that, we put an arrow on the end. Key distinction: this does not go on forever. In the past, we used arrows on functions, for example, to indicate its end behavior continuing on and on forever in a certain direction. With vectors, that arrow does not mean it's going on that direction. That's just specifying the direction the vector moved. So we put that arrow then there just to say, hey, it goes up that way, not down this way. Some people don't like to put it on the end just to symbolize the difference. You might see the arrow in the middle of that directed line segment. I'm used to it this way, so I put it on the end. And this is the vector we're calling V right now. So this doesn't go on forever. This is just the direction. All right, so we have a couple names for these. Since v, the vector v, started at point A, this is what we're going to call the initial point, because it initiated at point A. Since it ended at point B, we're going to call this the terminal point. It terminates at point B. So we have an initial and terminal point of every vector. I want you to take a second and practice this. Plot the following vectors on this same coordinate plane. So again, pause the video and try that out. All right, I did this already. Here is my graph of what you should have ended up with for each of those vectors. All right, so number 4, it's saying vectors can be described by their components. When I say components, I mean their horizontal component, v. I'm just going to do this in a little bit of color coding here. And their vertical component, or the horizontal component, we call this v sub x. So it's horizontal is the x direction, so we put a little x there. And their vertical component, v sub y. Just to specify that language, it's the vector v sub y, because it's a subscript. It's often how it's read. What it means is the vertical component in the y direction. And we use this notation here to describe a vector from its components. Notice that they're not parentheses, but they're angled brackets. The reason I use that is to distinguish between a vector and its and a ordered pair. So this is our component form right here, because it lists the components of this vector. There are several ways that we can write a vector. This is one of the more common ones, and we'll end up seeing different ways that we write it throughout this discussion of vectors. So let's look at v and write the component form of that vector that we graphed above. What we need to know is what is the vertical component and what is the horizontal component. So the horizontal component, v sub x, and what is the vertical component, v sub y. So let's go up and look at our vector v. All right, so right triangles are really what helps us figure this out. The horizontal component of this vector goes in the x direction. This is the horizontal component of the vector. The vertical component of this vector goes straight up. This is v sub y, the vertical component. Well, fortunately, we can actually count to figure out what those components' lengths are. The vertical, or the horizontal component, well, it goes from 1 to 4. Counted that, it's just 3. The vertical component, or sorry, horizontal component is 3. Vertical component, same idea. Count it, it goes up 1, 2, 3, 4. So the vertical component is 4. Therefore, we can write the vector in component form. V is equal to, we use these angular brackets. The horizontal component that we found was 3, and the vertical component that we found is 4. All right, same things apply for B, C, and D, the other vectors. I encourage you to pause the video and give that a shot right now. All right, and there is my work for it. Double check to make sure that you got the same things for the other three vectors. All right, continuing forward, we want to be able to calculate both the magnitude and slope of vectors. We're able to write the component form, so we can start to discover some stuff about them. So while graphical representations are useful, like we saw, it was easy to come up with a component form when we had the graph, just because we can count spaces. It's not always going to happen. Sometimes a graph might be out of the question. It might be huge. We want to be able to use just arithmetic to figure out things. So let's consider finding the components of the vectors without a graph. Write the component form of each vector. I should say of. So as an example, let's look at v. V goes from the point 2,1 to the point 5,3. So first, we need to figure out what goes here, our horizontal component. The horizontal component, without a graph, we got to look at our points in the x direction. So let's think. The horizontal component, what it's going to be is our change in x. Remember, delta, the triangle symbol, means change. This is the change in x, which means we have to take the x value of the second point and subtract it from the x value of the first point. This is x1, this is x2. So x2 minus x1 should give us the change in x. x2 is 5, x1 is 3. Sorry, x1 is 2. I was doing the math in my head already. Subtract those and it equals 3. So our change in x is 3. Turn this off. So our horizontal component is 3. Same thing applies for our vertical component. Find the vertical component. Instead of the change in x, this should just be the change in the y direction. It should be y2, the y value of the second point, minus the y value of the first point. y2 is 3, y1 is 1. So to calculate that, it should be 3 minus 1, which is 2. So the vertical component is 2. There's how we can find the component form without even using a graph. Could simply just look at the points and see, hey, it increased by 3 to get from 2 to 5. That was plus 3. And to go from 1 to 3, it was plus 2. Same thing applies. All right, so I encourage you to pause the video and try this out for these 4 vectors. And again, I did the work already. You should have found the following for the remaining 4 vectors. All right, number 2, the magnitude of a vector. We're going to call the vector v, is essentially the length of v from its initial point to its terminal point. So length. Magnitude and length can kind of be thought of as the same thing when we're talking about vectors on a plane. We use the notation v within 2 vertical brackets for the magnitude of a vector. some reason on my print it shows one smaller than the other. You don't have to do it that way. So if I were to write it by hand, this symbol represents the magnitude of the vector v. So let's calculate the magnitude of each of our vectors that we have up there. I'll do v as an example. To visualize this, I'm going to put it in a coordinate plane. Might not always be useful to draw a graph, but just to understand and come up with a way to do this over and over again without drawing a graph, let's do it once. So v is at the point, or is from the point 2, 1 to 5, 3. So 2, 1, there's our initial point, and our terminal point is at, nothing's drawn to scale here, it doesn't matter, 5, 3. So this right here is our vector v. I'll put the v up here. This length of it, that is the magnitude of v, from where it starts to where it ends. We want to be able to calculate that magnitude. This should look really similar to the work we did with complex numbers in polar form. What we're going to need is the two components of this vector. The horizontal component, v sub x, and the vertical component, v sub y. Alright, well, just by counting and what we saw up above, we know the horizontal component was 3 and the vertical component was 2. So our only unknown is this magnitude. On a right triangle again, you can use the Pythagorean theorem, which would say that the hypotenuse, which is the magnitude of the vector v, is equal to the horizontal component squared, 3 squared, plus the vertical component here squared, plus 2 squared, and then just simplify our equation. Still have the magnitude of the vector v squared. 3 squared is 9, plus 2 squared is 4. Sum those together. So the magnitude squared is equal to 13. Take the square root of both sides, and you should find that the magnitude is equal to the square root of 13. So we have just calculated the magnitude of our vector v. Seems kind of tedious that we have to do this over and over and over again, set up the Pythagorean theorem. So let's think generally. If I were to think generally, that means I am ignoring any of my actual measurements here, making v a completely arbitrary point, or arbitrary vector, I mean. So if we were to set this up, still be the same thing, just no numbers. So the magnitude squared would equal the horizontal component squared plus the vertical component squared. Then we would just take the square root of both sides because we don't know what v sub x or v sub y are. And we come up with this generic formula that we could really use over and over again. The magnitude of a vector, any vector, is equal to the sum of the squares of its horizontal and vertical components. Let's put that to use real quick. U. We know it has a horizontal component of -2 and a vertical component of -3. So to find its magnitude, should really just be the square root of that horizontal component plus this squared plus the vertical component squared. So again, I already forgot. Horizontal component is -2, vertical component is -3. So it should be the square root of -2 squared plus -3 squared. Square root of -2 is +4. Sorry, not the square root. -2 squared is +4. -3 squared is 9. Add those together, and hey, the magnitude of u is also equal to the square root of 13. All right, continue. Try to do B, C, and D on your own after pausing the video. All right, so there are our answers for B, C, and D. Double check to make sure that you got the same thing. Worth noting that for magnitude of S, we got the square root of 50, but the square root of 50 could be simplified because a perfect square is a factor of 50. 25 goes into 50 2 times, and we know the square root of 25 is 5. All right, when working in rectangular coordinate system, a vector's direction can be described by the slope of the line that it lies on. So let's recall how we can calculate slope. Slope, something we learned way back in middle school. We use the letter m to describe slope. Slope is just equal to the change in y values over the change in x values, which is y2 minus y1 over x2 minus x1. But what's really cool is we just discovered that this just gives us the horizontal component of a vector. Whereas this is just giving us the vertical component. So for a vector, all we really have to do to find the slope is take the vertical component and divide it by the horizontal component. So for our vector, v, as my example, we're looking for the slope of it. Well, m, our letter for slope, would be equal to its vertical component. Let's go back up and look at v's vertical component is 2, and its horizontal component is 3. It's just 2 over 3. So it should be really, really quick and easy to find the slope once we have the components of a vector. Give that a shot for the other 4 vectors after pausing the video. All right, there's my work for those remaining 3. It's worth noting that a few of them actually had the same slopes. So based on what we've determined, which vectors do you think are equivalent to each other? So let's look through. First of all, I noticed that a few of them have the same magnitudes. V was 13. I'll do this in a different color. V is 13. Square root 13. U had a magnitude of square root 13, W had a magnitude of square root 13, and R had a magnitude of square root 13. The only one that's eliminated so far is S. It had an entirely different magnitude, therefore it cannot be equal to the others. Well, look at the slopes. U had a slope of 3 over 2. It's the only one to have a slope of 3 over 2, so it can't be equivalent to the others. It had a different slope entirely. It's going in a different direction. W, R, S, and U all had slopes of 2 over 3. S had a different magnitude, so we can automatically ignore that. But right now we see that V, W, and R all had the same slope and magnitude. Does that mean they're all going, or they're all equivalent though? Let's look back up at our components. V had a component of 3 in the horizontal and 2 in the y. The only other one that's the same is R. That's how we can tell. Look at W. It's completely opposite. So if we were to draw these, V would look like that. W would have the same slope and the same magnitude, but it would be going the completely opposite direction. R would be somewhere else in our plane, going the same direction as V, but opposite W. Therefore, we can conclude that V and R are equivalent. Because they have the same magnitude and direction. So it's important to understand that just because the magnitude is the same doesn't mean they're the same vector. Or just because they're the same direction doesn't mean they're the same vector. Both the magnitude and direction have to be the same. Should be quick to tell if they're the same just by looking at the component form. If they have the same components, they are equivalent vectors. So it's imperative that we see that the components must be equal. Alright, and that's our introduction to vectors. We'll dive in even more as we continue through this and extend it further. Hope all is going well. Please come talk to me in office hours or tutoring if you have any questions about anything. Have a good one.